One of my biggest hangups when working with Arduino is plotting and processing data. It can be hard to see the plots, especially at high baud rates. The axes are always jumping around, and if I want to do something with the data, there's no easy way to store and post-process it. In my current application, I'm scanning a room using ranging sensors. On the serial plotter, I can see that objects are being detected. However, I can't get a sense of the spatial resolution. What I really want to look at is a 3D point cloud graph so I can see what the sensor sees. In the typical Arduino workflow, data from the sensors is read by the Arduino. Then it is sent through the serial port to the serial plotter. To process and plot my 3D point cloud, I'm going to read data into Python instead. In the first script, I'll read the data and save it to a CSV file. Then I'll write a second script that processes the data and plots it as a 3D point cloud. I've already written Arduino code to read data from the range sensors and write it to the serial COM. In the setup function, I set the baud rate to 115,200. The data headers are also communicated in the setup, so they are only written once. In the loop function, I read data from the sensors and then write each measurement to the serial COM. The measurements are separated by spaces, and a carriage return is used to separate lines of data at the end of the loop function. In this part of the video, we'll read data from the Arduino into Python and save it to a CSV file. If you're not familiar with Python, I've added a few links to the description that will help you to get started. We'll start the Python code by loading the necessary libraries. To read from the Arduino, we need to identify which serial port it is connected to. I'll call the COM_ports function to retrieve a list of currently connected devices. Then I'll loop through the ports and print each to the terminal. Here is the result. My Arduino Uno is connected to COM3. Before connecting to the Arduino, I'll open a CSV file where I can write the data. I'll use the truncate method to clear any existing data. To connect to the Arduino, I'll use the serial method. The first argument is the port, which I'll set to COM3. The second argument is the baud rate, which has to match the rate set in the Arduino code, 115,200. After connecting to the Arduino, we need to reset it. These functions will clear the serial COM and reset the Arduino. I'll read each line of data inside a for loop. For now, I'll only read 5 data points. Inside the for loop, I'll use a try-except statement to handle any potential misreads. That way, even if a data point is lost, the code continues to execute. Here I'm reading a line from the serial port. This is read in binary, so I'll have to decode it before I can save it. If there's an error, oh well. Let's test the code. You can see that the Arduino resets and then records 5 data points, which are shown here in the terminal. Now I'll parse the data and save it. I'll start by splitting the first line, which contains the data headers. This produces a Python list that contains the 5 headers as elements. For the rest of the lines, I'll use the split function again to break apart the string. I'll also convert the strings to floats. This isn't strictly necessary here, but if you wanted to do anything else with the numbers, you need them to be numeric. Now I'll write each line of data to the CSV file using the write row function. To complete the code, close the data file. Looks like it's working. Let's increase the number of data points so we can sweep over the room. As the Arduino runs, data is continuously streamed to Python, and Python is continuously writing that data to the CSV file. Here it is. Wow, that's a lot of data. In the last part of this video, we'll process the data and create a 3D plot. I'll use the pandas library to load the data, NumPy to process the data, and matplotlib to generate the plots. This is the reason I'm using the pandas library. It reads the CSV file into a beautiful table with just a single line of code. Each column of the table stores data for a single variable. For example, the second column shows the pan angle. You can extract the columns of the table, by converting it to a NumPy array, and then indexing into each column and assigning to a variable. Now I'll create a really simple 2D plot of the measured distances against time. I need to call the show method for the graph to pop up. Okay, this plot is a little too simple. I'm not even sure which line is which. Let's add a few more details. I'll add a legend, some labels, adjust the axis limits, and save the figure to a file. That's better. I can see there's actually a pretty large discrepancy between the two sensors. I wonder which one is taking more precise readings. To get a better sense of things, I'll create a 3D point cloud plot. First, I'll convert the data to Cartesian coordinates. The NumPy library has all the functions I need to do the conversion. Now, let's make the plot. The syntax is pretty similar to the 2D plot, but I have to let matplotlib know that I'm creating a 3D plot. I'll create point clouds using the scatter function. Setting the 3D limits is also a little different. And that's it. Here's the 3D plot with 16,000 points. This plot looks a little ugly. Adjusting a few of the matplotlib settings creates a much prettier picture. Here I've adjusted the appearance and exported a video that illustrates how the data was collected. We can see that this speaker was recognized pretty well by the time-of-flight sensor, and so was my monitor. The power supply, not as much. We can also see the ceiling, although it looks a little bent. Now let's compare the time-of-flight sensor to the ultrasonic sensor. In regions where the sensor hits the object straight on, the results are pretty similar. However, in regions where the sensor signal hits objects at an angle, the time-of-flight sensor displays good readings, whereas the ultrasonic sensor scatters all over the place.